last lecture of this short course. Today we're going to, get to the end of the things, and we are going to talk about the title of the course, actually, relativistic quantum fluctuation theorems. The main thing today is to join all of the 4 past lectures in a single thing. So to derive a relativistic fluctuation theorem for a quantum system that live on a curved spacetime. So under the action of gravity. That's the idea. I'm not going to the general problem because it's mathematically much more difficult, but I'm showing to you the simplest case. Anyway, the idea is there, and the results are there. And of course, we can discuss the general case if you want. But first, we need to start with the problem. What kind of problem we're trying to do. This is a little bit of thermodynamics and relativity. It started already in 1997, 98, just couple of years after Einstein published his special relativity paper. And of course, Einstein himself, Max Planck, and they tried to look, let us pick up thermodynamics and try to put into this context of special relativity. But the problem is that this is revealed to be an extremely hard problem. The difficulties, for instance, we needed to define equilibrium states. Equilibrium states, the zero law of thermodynamics, states that in a rest frame, all the net fluxes inside the body vanish. So this is equilibrium. This is the statement of a zero law of thermodynamics. One of the implications is that temperature is the same throughout the body. But for a guy that is moving with respect to this guy, to the system, this system will not be in equilibrium because you will see currents throughout the body. So that's one of the difficult things that you. And when you go to curvature space-time, then things get worse because you cannot define energy in different points. So we cannot compare energy in different points, and things get even worse. But we have this guy here that they concluded, both of these papers concluded that a moving body should appear cooler with a specific definition of temperature, because defining temperature is complicated also. Then many years after this, in this paper, they concluded that the moving body must appear hotter. So these things, don't matter. And then other guys, so no, temperature is a scalar, so must be Lorentz invariant. But no, if the fact is that we don't know how to define these things. But we have several developments linking gravity and thermodynamics. For instance, the black hole mechanics that we call today as black hole thermodynamics is one of the developments. Hawking radiation is based on thermodynamics. The asymptotic state of the Hawking radiation is thermal state, in the sense of quantum field theory, which we call KMS state. Then there is this paper, extremely nice paper by Ted Jacobson, where he derived the Einstein field equation as a thermodynamic state equation, which is very nice, this paper, actually. And then this is quite complicated paper. It's nice. I really like the papers by this guy, Carlo Rovelli, but usually they are a little bit complicated. This is one of them. He tried to derive statistical mechanics for general relativity, but it's extremely complicated, and there are a bunch of things that are not proven, and just ideas, which are also good because I like the ideas of this guy. And there is another thing, the statistical description of the gravitational field itself. So we know how to describe the electrodynamic field statistically. I mean, we understand how to do this, at least in flat space-time. We understand how to do this. Actually, the statistical description of electromagnetic field gave birth to the quantum mechanics. So we know how to do this. But we have no idea how to do this for the gravitational field. So this is another problem. We have two problems here. One is describe the statistics of things that live on space-time. The other one is describe the statistics of space-time itself. We are interested in the first class of problems. We are not going to the other problem because it's a completely different one. We will not touch on this, but these guys here, Carlo Orvelli, try to do this in these two papers, where he defined that time, put it that time has a thermodynamic origin. It's just the flux of the thermodynamic equilibrium state. This is what they defined the time here in classical physics in this paper and in quantum physics in this other paper. So it's very nice, but this is just a little bit that are reviews on the connection between thermodynamics and general relativity. There are a bunch of papers studying this thing. You try to, to give a foundation, mathematical foundation of into this problem. I mean, how to define the thermodynamics of things that live on a curved spacetime. Okay, that's a little bit of history. Well, that's the usual postulates of classical thermodynamics: equilibrium state, entropy. The entropy is additive, is infinitely many times differentiable, and monotonically increase with the energy. So that's the inverse of the temperature. So, but this is the fourth postulate. This makes us classical thermodynamics. So with this we can answer questions. These postulates actually they answer a single question. If I have a system, I change the symmetry of the system. What's the equilibrium state? That's the only question that these postulates are able to answer. So, macroscopic state. So, quantum thermodynamics. But this is a little bit more fuzzy. We have several approaches. Of course, quantum statistical mechanics, the first one. This book is a very nice book by Philip. I really recommend this book. It's a very new, 2022. Research theories, approach to thermodynamics, where they set up a set of states. In the case of thermodynamics, these states are thermal states, so they are not research of anything. And then you have you have infinitely many thermal states, and you have a few states that are not thermal. And the question is, what can I do using these resources, these out of equilibrium states as resources? So that's the main idea of research. We have research theories of everything: entanglement, thermodynamics, coherences, and whatever. We have plenty of research theories. And this one is a review on thermodynamics by Matteo Lostaglio. We have an approach that I don't know how is being developed today. It's based on density functional theory. We developed it to study many body systems. And it was developed by Irene and along with Roberto in Irreversibility Ce. We have axiomatic formulations of thermodynamics. The most beautiful one is this paper by Elliot Libby. This paper is really, really nice. I mean, I recommend everyone to read this paper because, well, it's a huge paper. It's almost 100 pages, but they drive thermodynamics here from logic. But they put a set of logical statements, and from these statements, they derive the thermodynamics. It's beautiful, beautiful. And then we have information theory. We want to discuss this guy, and we have gauge theory that I with some friends developed recently. The gauge approach to thermodynamics. Oh, by the way, it's is the topic of the colloquium that starts at 11. So these are just a few approaches on quantum thermodynamics. I mean, how to describe it, thermodynamics of quantum systems consistently. So the question that we want to study here is this thing. Just ask if there is any relation between the causal structure of space-time, what we saw in the last 3 lectures. I mean, the causal structure of that thing there, and thermodynamic irreversibility of quantum systems. I mean, is it possible to relate to these things? In other words, is it possible to relate to the causal arrow determined by GR, general relativity, with the thermodynamic arrow determined by that points to low to high entropy? That's the question. And we actually say that, yeah, there is a way to do this, and there is a natural link between these guys. These guys point to the same direction. They point to the same place. Okay, that's the main result that you have here. These papers are published recently here with Marcus and Jonas, that I showed a picture in the beginning of the course. And I'll mostly talk about this paper here, because the ideas are all there, everything is there. This is a special case of this guy, but this guy is much more complex, mathematically speaking. But the ideas, all the idea contained in this guy is here. I mean, just more complex and a more general result. So this is a special case of this guy. So I'm not talking about this guy except for the last 2 slides. Okay, that I showed the general result. But I mean, the idea is here. So quantum fluctuation theorem. As I told you, let us derive the quantum fluctuation theorem in the most general case. Now, because we derived it just, I mean, using unitary operations. Now we will open these 2 CPTP maps. Okay, and this is a very nice paper by Hastering and I don't know how to say the name of Carroll. His first name is Carroll. Okay, and we started the same way. The system starts at equilibrium state, defined by some temperature and some Hamiltonian. That's here, and then we measure the energy, and this results in this thing with this probability, and this is the energy eigenstate. So usual quantum mechanics, nothing different from quantum mechanics. All of this is flat spacetime. Okay, and then we let the system to evolve under a completely positive and trace preserving map, CPTP map. This can change the Hamiltonian, and some work is performed on the system or by the system. It doesn't matter. It's just a sign convention. So we made a final measurement, but in the eigenbase of this guy, because we went to determine the energy, and these outcomes with this eigenvalue with this conditional probability. So Born's rule. It just, this is the result of the first measurement that collapsed the state in a eigenstate for the initial Hamiltonian. Then we get evolved in the state, and then we get the second measurement. This is the conditional probability, and then from this we can compute the joint probability of getting both eigenvalues. Okay, usual quantum mechanic thing. And then statistical physics say to us that if I define these other variable, this is a random variable because it's a result of quantum measurement. This is another random variable because it's a result of another quantum measurement. So this is a random variable because it's a function of random variables. And then the statistical physics tell us that to change between the probability distribution of this guy, from these guys to this guy, is just like this. With delta is the Dirac delta function. Okay, just usual things. And this definition of work is discussed in this paper here by Peter Taucken and Peter Hang. They discussed these and some other measures of work. They don't match in general, but the actual definition of this guy will not matter for us. So let us use this thing that's most common one. And then from this, we can simply compute the average of the exponential of this guy, and I get Jarzynski equality. But Jarzynski equality that you saw in the first lecture was just this term, just this one here. Now appears this other guy. This other guy, this is the thermal state defined with respect to the final Hamiltonian. This omega here. This other guy, G, is this operator, where rho star here is the maximum mixed state. So these, if the map preserves the identity, the energy, the evolution is unital, then this is zero, and we get usual Jarzynski equality. But if the map doesn't preserve the identity, then this is different from zero, and this is going to be a correction. So if I have an amplitude dumping, for instance, it does not preserve identity. So this is just a correction due to the lack of unitality of the map. But the structure of is exactly the same. Okay, so that's the general Jarzynski equality. Is it possible to derive Crookes relation also? We just need to define the same thing, but the backward direction, and then we divide it one by the other, and we get the Crookes relation. Integrating, we get this guy. Mm-hmm. Yeah. Is this thing? So the work is the work by the map. It's performed by the map. We don't consider the measurement. I mean, the measurement is just to establish the map on the system, or on the system or by the system, depend. Yeah, yeah, yeah. But this is a convention, no? Oh, that's easy. That's easy. Um, ca- can you see here? Yeah. Let us suppose that I have a Hamiltonian that's time independent. Then I make the first measurement. When I make the first measurement, I will evolve. I will evolve according to this guy. T. But after the first measurement, I get an eigenstate of this guy, so nothing happens. So for something to happen, this guy must be time dependent. And if this is time dependent, it means that you're describing your system effectively, because you are changing the energy, you are putting the energy in some way there. You are putting a laser, and you are not simply consider that the laser is plugged into the wall. So that's the work. It must be time independent, otherwise nothing happens. Well, that depends on the definition of closed systems. No? By closed, we mean that's not exchanging energy except for a time dependent Hamiltonian. Isolated means that the Hamiltonian is time independent. So nothing happens with the system, it's just under its own dynamics. Yeah. No, but you are doing your work actually. Let us think about a quantum system, and you are applying some laser on the system. The laser is a classical thing. Um, how do you describe the action of the laser? The action of the laser on an atom, for instance. We have the Hamiltonian of the atom, this guy, a two-level system, plus uh, uh, you. The simplest case is this. So this is the simplest possible interaction of a laser field, classical laser field with atom. But this is effective Hamiltonian. You are injecting energy into the system. Yeah, yeah. But that yeah. Yeah, but with the time dependent Hamiltonian. It must be. You must perform work on the system because of this thing. If you don't do this, then and the only way to do this is to act on the system. Classically, it's you are performing, you are applying a force on the system. Quantum mechanically, that there is no force, but we can write a time dependent Hamiltonian, and that's it. That's it. With some yeah what yeah yeah yeah. There are no time dependent Hamiltonians in theoretic picture. If you have one, this means that energy is not being conserved. This means that you are describing a system effectively. It's not the Hamiltonian of the system, but it's the effective Hamiltonian of the system, like this one. Yeah, that's the point. Yeah, yeah. Like yeah, yeah, like the sideliner of the piston. To perform work, you have to push. That's the but in physics two, we can actually describe the force that you are applying the system here. It's just time dependence in the Hamilton. And Jasinski, yeah, yeah. The Crookes fluctuation relation, yeah, 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 yeah. And then you integrate. Yeah, yeah. Crookes is called today as detailed fluctuation theorem because it's a statement on the probability, and this guy is a statement about averages. So it's just integration of the other. It follows from integral. Yep. Yeah, exactly, exactly, exactly. I'm gonna show you in the last slide because it's a little bit complicated, but it's the same form, but it's a little bit more complicated. But we have the same thing. We have Crookes and then follow this guy. But the main idea is here. What I want to show is here. That's the is what we did in the first paper. We did consider the simplest possible thing. It's a quantum system that is under the action of Newtonian potential, and we want to study the equivalence principle. The consequences of not being following geodesics. What happens? So if I follow geodesic, then nothing happens because I'm just free falling with the system. Nothing can happen because I know that nothing happens. But the question is, when I deviate from geodesics, what happens? That's the point that we want to study, and this is a little bit more complicated. So we needed to establish our system. That's the first thing that we need to do. General relativity. This is, for me, is the best book in general relativity that was ever written, and it's amazing. This book is amazing, but I don't recommend this book for the first reading. It's extremely heavy, but and by the way, these guy also have a book on electrodynamics, which is Jackson, but that size. So this is complicated, but it's beautiful. It's beautiful. So we assume that we have this guy. This is a manifold, the space-time, and this is a Lorentz metric defined as a manifold. So this is just what we saw, and I put this special thing here. This means that I can foliate the space-time into spacey hypersurfaces and defining each point the future direction of time, which is perpendicular to the space hypersurface. I need to do this in order to do physics. If I can do this, we call these sort of spacetimes global hyperbolic. So this is a property called global hyperbolicity that we need. Why we needed this? Because on these hypersurfaces, space hypersurface, we define the initial conditions of our problem. And the dynamics is given the direction of time. So if we're not able to do this, we're not able to define the initial conditions, we're not able to solve the dynamic equations, everything is lost. So we need to assume that this is true. Apparently, our universe is like this. Our space-time is globally hyperbolic, and we can define orientability, at least locally. Okay, so we assume that this is true. And this is extremely important for us because I think that's problematic here. If I cannot define time, I cannot define temperature. If I cannot define temperature, I cannot define thermodynamics. So all of this is lost. So that is a very nice discussion, this paper here. These two papers actually, about definition of temperature in terms of orientability of time, because it is still a debate, this thing. There are people that like, there are people that don't like. That's why we need a mathematical structure behind of this thing, because with physics it's easy to discuss, but against math it's a little bit more difficult. You need to prove that the math is wrong, and then this is a little bit harder. So that's our field, and we do this in Newtonian limit, which means extremely weak field. Okay, static field. So we just want to see the action of the Newtonian potential in these things. So that's the gravitational field that we are talking about here, the simplest possible one. And then matter. Matter is just a quantum system where I have a Hamiltonian for the particle and some internal structure. And this part, why do I need this thing? Because I need to define trajectories on these space-time. In order to define trajectories, this guy must have a classical degree of freedom. We can think about star-galaxy experiments, for instance. Star-galaxy experiments, the only way to understand that thing is when I put a classical trajectory to the atom. The spin is a quantum degree of freedom, but the atom is classical. It follows a classical trajectory interacting in a classical electromagnetic field. So here's the same thing. We have a classical thing whose internal degrees of freedom are quantum. Okay? Because I need to describe this guy. This puts a limit on the theory that we cannot have huge superpositions. Here we have it because the space-time is quite particular, but in the general case we cannot. But I'll talk about this later on. So these are the assumptions that I made here. Okay, this sort of field, the gravitational field, and systems. Find the Hamiltonian. The symmetries of the system includes the time-like killing translation. So, and who does translation time? So that's the time evolution. Because time evolution is governed by the Hamiltonian, And this guy is the symmetry along time evolution, along time direction. So it's this guy that is important for us. So, and we define static observers to this guy. So static observers, they are static in this space-time if they follow this guy here, the time-like killing field. They're just following this direction. So I'm following direction of time, just this. Okay? And the velocity, the guy will be this one. And this is just, I mean, the vector pointing the future direction of time. That's the killing field. Okay? The time-like killing field. So that's the way. You see that we need you to define all of these things, otherwise you cannot define a Hamiltonian of the system. That's why it's hard, it's very hard to work with the quantum systems on curved spacetimes, because we need to take care of all of these details. Otherwise, I mean, the definition of the Hamiltonian. Some people say sometimes you pick up papers that put, oh, we have a Hamiltonian, we have a Hilbert space, and that's it. But you need to define these things, otherwise it makes no sense. These things make no sense. They are just words. So, and these guys, all of the guys that follow this thing defines a class that we call laboratory framing. So that's the guy that's making measurement. The guy that's performing measurements following this thing here. Okay? And we define thermal equilibrium with respect to this guy, because he's making measurements. So thermal equilibrium must be defined with respect to him. But to define the Hamiltonian of the system, we need to go to the moving frame of the system, because the system can move. If I describe the system from my point of view, the laboratory point of view, what happens is that due to gravity, the internal and the external degrees of freedom of the system will get coupled. And I don't know how to describe the Hamiltonian. So I need to go to the reference frame of the Hamiltonian of the system, define the Hamiltonian there where the system is at rest for me. And this is always possible, it's just a coordinate transformation. I can always do this. It's arbitrary. It doesn't matter the motion of the guy, because I'm dealing with general relativity. I can do whatever I want. So there I can define the Hamiltonian, which is just the Hamiltonian of the external plus the Hamiltonian of the internal degrees of freedom. And then I come back to the laboratory frame, and then it gets coupled. But it is a different thing. But I need to go there, otherwise I cannot define the Hamiltonian. And then we consider a metric, which is the static metric. That's the most simplest case we can get, where this guy is just Newtonian potential, and the other guy is Euclidean. Okay, just Newton thing. I don't know a gravitational field that's simplest than this one. We tried to solve the problem, the general problem from the scratch. But then I see, no, look, things are not that easy. Let us start with the simplest possible thing that we can do. Otherwise, I mean, it gets complicated because of all the things. So we get the field, we get the system, we get a Hamiltonian. This is the classical Hamiltonian of the system. It's just the external degrees of freedom, with just the rest energy of the system. C, the speed of light is equal to 1, so it's just m. That's the rest energy of the system, the classical thing, and the internal degrees of freedom with whatever. It can be whatever. So this is age in the laboratory frame. So we go to the laboratory frame, we make the change in reference. What appears is this guy. So tau is the time of the in the reference frame of the system, the proper time, and no, t is the system, and tau is the proper time of the guy. So this is how time changes, how time measurements are related between these guys. And this simple case, very simple case, the only thing that I expect is this. What's this? What does this mean? One is flat space-time, nothing happens. Not even special relativity. This guy is the special relativistic correction, with special relativistic time dilation, because it depends on the momentum of the system. If the momentum is 0 with respect to me, the guy is not moving with respect to me, and then I don't have time dilation. This guy is the gravitational time dilation. Which is what we call gravitational time delay. So we want to study the contribution of this guy coming from this guy. What does this mean to thermodynamics? Okay. Okay, then once I have the system is defined on that hypersurface that I told you. I have do you understand that I need the future direction of time to define Hamiltonian? I mean, is this statement clear? Because, I mean, in general, how do we define Hamiltonians? We have a space-time that we don't know what it is. We don't know how to make calculations. We don't know how to define things there. But we know Nader's theorem. M. Nader taught us that to every symmetry, you have an associated conservative charge in the system. And the time translation symmetry of the system is associated with the Hamiltonian of the system. So we define a Hamiltonian by defining time, the future time direction. Then we compute the Nader charge in that direction, that's conservative in that direction. That thing is the Hamiltonian of the system. That's the way we define Hamiltonian. That's why we need time to define Hamiltonian. Otherwise, we cannot define this thing. And as you remember, time is a little bit difficult thing in general relativity. So these things must be properly defined, and we must need to take extremely care on these things. Once you have the quantization of these things, everything is quantized here, because now I have everything defined. Then I just define it at some initial point of the manifold. I define the initial stage. It's just the external degrees of freedom and the quantum degrees of freedom, internal degrees of freedom. So just use Hilbert space. Exactly. It's defined by the time direction. Yeah. Is the Nader charge conservative in this direction? So you see that if you have a different killing fields, you have to define different things. Exactly. And to define the initial conditions, this guy here, I defined it in this hypersurface, because you hear this 0 here is t equals 0. So I pick up one hypersurface that I call it arbitrarily 0 t, and define my state here. That's the initial condition of that the Hamiltonian will evolve. So I need to define these things, otherwise there is no way. And those papers that I showed by Carlo Rovelli, they discuss it beautifully. Discuss it actually, the notion of what they call thermal time that is responsible for evolution things, and they're very nice. So once you have all these things, all of these things defined, and I have the Hamiltonian and I have the initial state, I'm assuming Schrödinger's equation hold. So it's just beyond those assumptions, I'm assuming that locally Schrödinger's equation hold. So it's not fully relativistic, the system, because it's Schrödinger, but I'm assuming locally quantum mechanics holds. So to compute this thing is easy. It's just usual thing. This guy. The first equation said to me that I don't want a time-dependent Hamiltonian. Otherwise, it must be a time operator here. Time ordering operator in front of this guy. So I'm disregarding time dependency. But then comes our question. See, if I put here a time-independent Hamiltonian, nothing happens because of the first measurement gives me an eigenstate of the Hamiltonian, nothing happens. Yeah, that's true. But we must not forget that we have a gravitational field beyond these things. And the gravitational field is changing in position, not in time, but it's changing in position. So the question that I want to see is that if I do nothing on the system, absolutely nothing, the evolution is unitary. What's the consequence of the system living in a gravitational field? In the appendix of the paper, we derive the full thing with time dependence here. But if I put a time dependency here, what happens is that more entropy will be generated. But this entropy will be generated by this thing that we already know how to deal with. It's just you are doing something on the system, not just the gravitational field. I just want the effect of the gravitational field here. Okay? Well, because I'm assuming that the Hamiltonian is not time dependent. Yeah. No, it doesn't. Because the t is the parameter on the curve. I'm integrate this integral is performed on gamma. Gamma is the trajectory of the laboratory. No, because I have a trajectory there. I have the gamma which specified is the trajectory of the laboratory. I'm just doing this integral over this curve, which is oriented by time. Just exactly. Oh, I see. Oh, no. This is the parameter of the curve, and this understand this as going. I'm integrating over the gamma from 0 to t. But of course, I need change this thing. Think of a prime here, because the integral is not the same t. You are right. I mean, yeah, the t is the end point of the integration. Yeah, did you get it? It's just, I mean, think of this guy as a prime here. So t is the end point of the integration. I'm integrating from 0, which is the start point, to t. Yeah, over the following the path gamma. And remember that the killing field that I defined is tangent to this guy. It's tangent to gamma. Yeah, so I'm just following this guy. The end of some time as measured by the guy. The clock of the guy that's following this curve. Not the system is different. But so here is just me opening the Hamiltonian, and here's another approximation. I just said, no, this guy is not an operator. It's just a function, because it's a classical degree of freedom. Of course, I can take this guy to be quantum also. It's harder to do the calculations, but it's going to be the same. And then we allow superpositions of this guy, small superpositions of this guy, and we can study how gravity affects superposition. And what happens is that gravity will destroy superposition. And the intuition is very, 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 very simple, because if I create a superposition at some point, and then the guys go here, the endpoints of this guy will depend on the trajectories or the branches of superposition. This means that some information about the system must be in the system, must be in the gravitational field. So if you lose information, these guys decohere. It must. Otherwise, it will be path independent. Okay? So we don't want to see this effect. We just want to see the effect caused by this guy, just the gravitational field. So we are eliminating all other things. In the sense that if you put this guy 0, then nothing happens. Absolutely nothing happens. The system is just there. So we do exactly the same thing, initial setup. Our P point in the manifold that starts there with T equals 0. And then the internal energy we can write this way because we can choose this guy like this. And Newtonian potential is absolutely arbitrary. I just choose the reference here. You can choose whatever I want, but just the reference, I put 0 here. And then the evolution is extremely simple because of the Hamiltonian is just, a displacement, a time dilation. And then I computed the eigenvalues, the eigenvalues, the final eigenvalues at time tau is just, this guy, which is expected because it's just time dilation. It's time dilation due to special relativistic and gravitational time dilation. This is actually what happens. This is when I'm climbing the gravitational potential, what happens is that redshift. So this is redshift, gravitational redshift, and special relativistic blue or redshift, depending on the direction of the moment. Okay, so it's the simplest possible thing we have. And this actually was already measured. And this is why we clocks run appears to run slower when you go down into the gravitational field because of this time dilation. It's very, very simple. Then we proceeded the same way. The system starts at thermal equilibrium, defined by the guy, which holds the clock. But the problem is that since we assumed these symmetries of the system, we can do this in every point in space. This will not be true in the general case, but here it is because of the symmetries of the space-time. I can foliate the entire space-time. This is just a property of this guy. So everybody that is standing in this guy will define the same temperature, the same reference system. And then always from the point of view of the guy, not from the system. The system, I don't know what's doing. The system can be doing whatever. The only restriction is that the system must meet the guy twice. The trajectories, the trajectory of the system and the guy must meet twice, because the guy must make measurements on the system, so they must be at the same point in space. Usual projective measurement. The guy performs a projective measurement, let the system evolve, and then second measurement. Just this, but we let the system evolve just by living on space-time. They're doing nothing else. Think about harmonic oscillator. The harmonic oscillator is just there, oscillating. Nobody's doing nothing. It's just oscillating on a curved space-time. It's moving in the direction of time. Okay, and also in the gravitational field. So we define the work in the same way. It's just, in our case, it's just easy like this, because just time dilation. This here? Oh, because of this. The final eigenvalue is proportional to the initial one. It's just time dilation. This will not be in general the case. If this guy has time dependence, and then this will not hold anymore. But this, as I told you, is the simplest possible thing we can do. So that's why the delta appeared here. And then, given this definition, we can simply define the probability of work, probability of this guy here, and compute the same thing. The difference is that now this average depends on the path. Actually, depends on the relation between the two paths, the system and the guy. And then from here we get the second law. That's just the statement of the second law of thermodynamics. If I live in a moving free falling observers, which means that I'm just free falling with the guy, then this guy is equal to this, and this guy is equal to 0, and we have a trivial statement. And free energy doesn't change. We expect that because I know if I'm free falling, just special relativity holds, and since the guy is standing, so there is no momentum, so there is no correction. Nothing can happen in this case. But we have these two cases. I mean, energy blue shift, falling down, or energy redshift, climbing the gravitational potential. It's just a convention when we do the things. This guy is negative, but the work also changes signs, and then you have this relation holds depending on the trajectory of the system. So these results published here. This was the first. So the idea here is all here. When I have a classical harmonic oscillator, it's just a harmonic oscillator system. The internal degrees of freedom. It's just a harmonic oscillator, and then computed the change in this guy appears this guy. So if this guy is not 1, which means that no gravitational correction, no special relativistic correction, then this guy is 0, and everything's okay. Nothing happens as it should. But when the momentum is 0, we still have a correction of the gravitational field here. And in this case, extremely simple case, we can interpret the work as the difference in the gravitational potential. That's the initial point of the system, that's the final point of the system. In general, this will not be true, because in general, work is not equal to the potential. I mean, this is the case also in electrodynamics. I mean, the scalar potential in thermodynamics, the change in scalar potential is not related to changing energy in general. It's a different thing. Since the scalar potential is just a part of the four vector potential, which just, a gauge field. You don't care about these things. But in this case, you can interpret the change in the gravitational potential as the work. And it can be positive or negative if you are climbing or going down in the gravitational field. So the idea here is that the main message is that just for you to live in a gravitational field, because you are moving in a world in which the metric is changing, entropy will be generated. You are going to see entropy generated. So this is because of the causal structure of the space-time. But how do you see this in general? In general theory is much more harder. I will not show all the calculations here, but hopefully you follow the idea of the general theory. The general theory is because of this. We know that now time must be defined locally, and everyone defines his own time. So time is actually gravity has no time there. Once I give you the metric, everything is there, and there is no sense of time. Time appears when we living here and having access to this guy here and can influence these guys here. We start measuring using our clocks, local clocks. We don't have access to the entire space-time, but just locally. But locally, we can define time, and then we see time appearing. So that's the notion of time that we have. That's physical time. The other one that t that we have in a metric is not physical. It's just a coordinate thing. It means nothing. What it means is that time that we define here locally. But this depends on the point that you are. This depends on the gravitational field. That's why this guy will define different things. Okay, and this time always goes in this direction, in the future direction of future light cone, but your light cone, not any other else. And this depends on the state of motion and depends on the state of the gravitational field and everything else. So how do we do this in general? Well, in general, it's much more harder, but we make the same assumptions. Locally, quantum mechanics hold, and statistical mechanics hold. General relativity holds in general. And what we do is that we create in a small region of space, we foliate the space. This is a space hypersurface, but it's small because I cannot do this over throughout the entire space-time. I simply cannot do this because I cannot define time here. The vector that's perpendicular, that's tangent to this guy is time. Time for this guy. So the black curve here is the laboratory frame. So what's time here? Time is the time that the guy in the laboratory is looking at the wall. As the clock measures, that clock at the wall measures this time. And this is the trajectory of the system. I mean, it doesn't matter what it is. It's some trajectory. What's important is that it has classical external degrees of freedom because I need to define this guy. And I need to define this guy because I need the trajectory, because the trajectory defines how the system interacts with the gravitational field, which is local. So I need to define trajectory. And the laboratory frame is here. That's the initial thing, that's the final thing. How do we do this? Well, we define this guy here, and then you choose special coordinates here. And there are the thing is that there are a very special reference frame here, it's called Fermi coordinates, where you can actually define this space, and using this guy, you can define Hilbert spaces here. So you can define Hamiltonians here. And this is even more special because I can pick up Fermi-Walker parallel transport because I need to transport things. From here to here, I need to transport things through spacetime. And if spacetime is curved, we saw that things are very complicated. So we need to use parallel transport. And there is a very special class of parallel transport that's Fermi parallel transport, which takes the reference frame from here to here consistently. So use this thing to move the entire reference frame of the system and to evolve the system using Schrödinger's equation. But here, it means that the system cannot delocalize it too much because these calculations are only valid here. And we pick up the geodesic distance from here to here with space-like. And we make expansions with respect to this guy. So we linearize the space-time with respect to this distance here. If the space is too curved or the system delocalizes too much, the calculation breaks down. Okay, is it clear? The blue one? No. Is the space is a space hypersurface perpendicular to time. So if I draw a time vector here, it's going to be perpendicular to this guy. Then I choose Fermi coordinates in this guy because I need to choose coordinates in the same way you just did. Yeah, exactly, because I have a coordinate system there. But this means that I have to consider a very small portion of space. No, this is a local reference frame. This is local for the... Who is defining this reference frame? The guy that's laboratory. This guy is defining the reference frame. And the blue surface? Yeah, exactly. I mean, I'm just doing the reference frame that we did in special in general relativity. I'm just linearizing that part of space-time. And how do we do this? We build, I approximate this guy, the space-time, by a tangent vector, space. And then I can choose whatever coordinate I want there. And I choose Fermi coordinates because it's appropriate to do calculations. Sorry, come again? They are small region, and smallness in this respect. I mean, we define the geodesic distance from here to here. Actually, that are plenty, and we say, look, this the size of this guy must be smaller than the curvature radius at that place. So it's the same idea of defining, um, approximating a small portion of the sphere to a plane. So how small is this? Well, depends on the curvature radius that we have. Just a minute. That's why this guy, from here to here, it cannot delocalize too much, because otherwise it will get out of this approximation, and then the calculation breaks down. So that's a restriction on that sort of system that respects this thing. Geodesic? Yeah, exactly. It's a geodesic coordinate ball. It's exactly this. And then we expand the metric in terms of this geodesic distance. Because I mean, we cannot do the calculation in general, but expanding the metric in Fermi coordinates, we can do this. Space-like geodesic ball. This guy. Yeah, that's it. And then we can define a Fermi Walker transport that takes us from here to here. Which gives us takes the reference frame from here to here, so I can compare vector spaces, because the vector space here is different from the one here. It can be completely different, but I know how to compare things. Parallel transport. And parallel transport, Fermi Walker parallel transport, makes this transport very special, because it takes the reference frame from one point to the other, keeping the orthogonality with respect to the time direction. That's a special thing. So the time direction that's defined by this guy is always orthogonal to the hypersurface, to the space hypersurface. That's the job of Fermi Walker parallel transport. If you use another one, then this relation can change, and then you lose the space, the Hilbert space. You cannot define Hilbert space. So you need this thing. And then by doing this, we define the forward process, and then we define the backward process, because we have the tool, the mathematical tool to do this. Just apply the time reverse operator here to the dynamics, and we go from here. So we define it in the same way we did the forward thing. We define the backward probability, and then I just divide one by the other, and I have this thing. It's exactly the same form, except for these labels here. Oh, there is a comma here. Oh no, this comma is here. This depends, the probabilities here depend on the trajectory of the system and the trajectory of the guy. That's the difference. So they are not that beautiful to see, but I mean, they are computed in the paper. And then integrating this guy, we have this guy. So this relation is highly dependent on the relative trajectories between the guys in spacetime. That's the important thing. Let us see an example that I showed to you. Do you remember yesterday the metric, Robertson-Walker Friedman metric of the expansion of the universe? So we just consider harmonic oscillator. Of course. No, alpha no, alpha no. Alpha is the trajectory of the particle, like the star galaxy. Is the trajectory. It cannot be too much delocalized. So if the system evolves and the internal degrees of freedom start delocalizing, or the external degrees of freedom start delocalizing, then you break down. At certain point you break down this relation, because okay, these holds under the condition that both trajectories keep inside this tube. This tube is defined by the Fermi-Walker parallel transport, and this is called Fermi tube. Both must be there. Otherwise it breaks down. Oh, I'll get there. Wait a minute. Quantum field theory is different. That's why um, I told you that this is not the full relativistic thing, because this guy is not relativistic. It follows Schrödinger's equation. It's not delocalized. The full thing we need to solve for quantum fields. Then there will be no problem. Okay. Yeah, that's it. That's the main result, actually. That's the main result of the paper, is a detailed fluctuation theorem, which implies Jarzynski. Then we just consider the simplest possible thing: a harmonic oscillator, just living in an expanding universe. So the trajectories are very easy. I should put a picture here, but anyway, that's the trajectory of the observer, the gamma, and the harmonic oscillator, just this is p, this strange p. Just go this forever. That's the straight line is the trajectory of laboratory, which is just standing, and the curly line is the trajectory of the harmonic oscillator. But while the guy is oscillating, the universe is expanding. So the metric is changing in time. How it's changing? Fermi, Friedman, Robertson, Walker metric. But here, written in terms of the Fermi coordinates, and up to second order in the geodesic distance. So I just expand the metric and compute the line element of this guy, and this is the metric. What happens is that the probability distribution is a function of the Riemann curvature tensor. So you have a specific explicit function that relates the probability distribution with the Riemann curvature tensor, so with the curvature of the spacetime. And then when you compute these things, if you just let the harmonic oscillator live in here and nothing is done on the thing, there will be no transitions. Transitions between energy eigenstates indicates entropy, because indicates irreversibility of the system. So if you are living in a flat space-time, no transition, nothing will happen. So the only thing that we need to compute is the transition probability. If these guys are not zero, then we have entropy being produced. In the paper, we computed the entropy also. It's not a beautiful expression. It's in the appendix of the paper, but it really doesn't matter. What matters is this guy. And this guy is given by this guy. This is just usual quantum mechanics. But this guy is Hubble constant. So it's proportional to the Hubble's constant. This implies that on average, entropy will be produced in the system. I mean, I just consider a simple harmonic oscillator living in a expanding universe. Because the metric is changing, entropy will be produced by these, as seen by this observer. If I change the observer, I change the relation between gamma and alpha, and I change this amount. So this metric, I don't know if you remember, but we derived the metric in a very specific coordinate system, which is the comoving frame. The guys that are comoving with expansion of the universe. If I change this point of view, these change. And this is expected to hold because if I just free falling with the guy, it doesn't matter the gravitational field that we see there. I'm just free falling with the Hamiltonian or the harmonic oscillator. Nothing should happen. I cannot see any entropy being produced because the special relativity holds, then nothing happens. And this is the case. So this happens for these guys actually that are an entire class of observers. So in this sense, and from where these come from, because the time relation between these guys are different. So they will see different things. And that, I mean, unless you are, and there is no way for this guy be negative. I mean, you can prove that there are no trajectories, We prove it there. There are no trajectories, no possible motion, no possible gravitational field that makes entropy production negative, on average. So it's always positive, it's always well-defined, and it's zero only in free fall, when both are in free fall in the same reference frame. Then it's zero. Otherwise, you're going to see entropy being produced in any system. And this is because you are inside the light cone, and you cannot you simply lose information that lies outside the light cone. But that is there. It's there in the gravitational field, but not for you, because you don't have access to this thing. This is very simple to understand. Think about a photon that hits you and goes away through the window. The information carried by the photon, is lost for you forever. You cannot get back that information, never, because of causality. It's impossible to get back. This is the source of entropy. Because we live in a universe that is causal and that we don't have access to the entire universe. Mathematically means that the thermodynamic arrow of time points in the same direction of the causal arrow of time, causal arrow. So they point always in the same direction, which was discussed by Carlo Rovelli actually in this beautiful paper. I recommended this thing. One day I would like to be like this guy. I just put papers on archive and not publish. I mean, don't care to publish papers anymore. Just put that on archive. But it's a beautiful paper, this thing. So he discussed some things like this, and especially this thing here. I mean, the thermodynamic arrow of time, he argued actually, that's rooted in the causal structure of the spacetime. So that's the argument of the guy. So it's deeply linked to the arrow of causation. That's a very beautiful paper. What you did here was to prove this statement. So that's the main result. I didn't show you the calculations, but I hope that it's clear how it's done. And of course, if anyone wants to go into the details of the paper, just knock on my door. I'll be here for a month yet, so we have plenty of time to discuss these things. And it's going to be a pleasure to discuss these sort of things. And then we finally have this final meeting. Okay, that's Einstein and Boltzmann. The arrow of causation and the arrow of time. Okay, and so future, whatever future means. There are applications to this guy. Like, let us consider now space-times with event horizons, black holes. What happens? What happens with these fluctuation theorems when you throw a particle into a black hole? It's a direct application of this guy. It's just, pick up the metric, define a decent coordinate system. Well, this cannot be too easy, but and compute the things and see what happens. And then this is very important, the data fluctuation theorem for quantum fields, because then we have a full relativistic theory. Well, but early in this week, I had a meeting with my student, and he just got the result for quantum fields. So we have the difficult thing here was to define projections, energy projection in the field. This is extremely hard to do. So we did this for a special case, static spacetime. Now is his PhD job to extend this to general spacetime. He likes to do calculations. Also, relativistic corrections to uncertainty relations, especially time-energy uncertainty relations. These, I think, is direct computation. Since we have the time evolved state, we can direct compute these things as measured by the guys in the laboratory. Right? Some other thing that enters here is particle creation, because when I have a quantum field on top of a spacetime and the metric is changing, then particles will be created in the field. This, as we showed in this paper here, generates entropy. So the state of the system goes to thermal one, because of particles is being generated and more than these. generated and scattering between all the modes. So the result that my students get here is just contribution coming from the interaction of the gravitational field. But we needed to take into account two other contributions. One is the entropy generated through particle creation, which we cannot avoid. We cannot turn it off, this thing. We have a quantum field. And the other thing is the generation of entropy because of the detector. Because the detector is just a classical system with internal quantum degrees of freedom living in quantum space-time. We just saw this generated entropy. So we needed to understand how these three contributions that we cannot simply avoid enter into the game. And this is a little bit in the future to understand, but we know how to compute the three contributions. We just need to put this into a single theorem. This is, is a thing that I would like to understand one day, if it's possible to learn something about the statistical description of the gravitational field. The question here is, I don't know the answer. If under this formalism, I can study the statistical description of the gravitational field itself. I don't know. But I would like to understand these things one day. And also, if the gravitational field is quantum, what do I mean by this? I mean that in a very weak field limit, I can describe gravitational waves. I can quantize these guys. I can make an effective quantum theory for the gravitational waves, and these fluctuate. And these, as we show here, generates entropy. So if we put beyond these contributions here, these and the quantum field and the detector, we still have the quantum contribution of the gravitational field itself to the entropy. So the idea is to join all of these things in a single thing. But here is limited to the weak field limit, because otherwise I don't know how to describe the quantum degrees of freedom of the gravitational field. Okay, and with that, I thank you all for the attention, guys. So, questions? This last question key over. It's, well, if I'm just free falling with the system without doing nothing, it goes to zero. It goes to zero because this guy goes to zero. Oh, the upper bound is the dimension of the system. The log of the dimension of the Hilbert space. That's the upper bound. So for quantum fields, we have an infinite quantity. Okay. Oh, no. This holds this holds in that entire tube. This stop holding when we break down the approximation. Then stop holding. In the theory of quantum fields, you don't have this limitation, because quantum fields, they live in the entire space-time, and that's it. Just the measurements are local, but we have the same restriction for the detectors. But the detector makes sense. I cannot have a delocalized detector. This would make no sense. So this is okay. Oh, yeah, Hubble constant. That's curvature. Hubble constant is just, I mean, this guy. These guys, the square of the Hubble constant. Well, that's not, it's far from being a naive question. Um, Actually, is a thing that I actually have a meeting with a student of mine now this afternoon to discuss this problem because there is I mean there is a question that um, um, let us put, no, what you are asking is that if I'm these papers here, we studied quantum fields on top of a space time. And then I asked this guy, Thiago, say, look, let us look for the correlations in the quantum field that we can know how to measure. Let us see from these measurements of correlations of the quantum field, can I understand? Can I learn something about the underlying metric? And the answer is yes. It's possible to do this. We found some papers, quite a few papers that relate to these things, these quantum fluctuations, quantum correlations, which are just Whitman functions, with the metric, the underlying metric. No, it's Adrian Kench and some other guys. This is, and then there is another paper by Masahito Ueda where he derived the metric, Fisher metric, which means the metric in statistical manifold, by means of a fluctuation theorem. Yeah, fluctuation theorem in general, as you saw in the beginning, the very beginning of this course, is stated in terms of a correlation function. And this is true also in quantum fields. So what I asked Thiago was try then to relate the Fisher metric with the spacetime metric. And then we have an informational description of the spacetime. And we do this through the correlations, the field correlations, the Whitman functions. So this is not as far from being naive. Apparently, it's possible to do. But I don't know. I mean, we have to do the calculation because Fisher metric cannot be equal to the spacetime metric because Fisher metric is Riemannian. Spacetime is not. So they cannot be equal, but they can be related. And apparently, the relation is through fluctuation theorem. Oh, crazy. Yeah. What, what do you mean by this? Oh, yeah. Actually, in this paper here, um, mm, yeah, probably yes. Yeah. What we saw in these two papers here, where we considered also particles with internal structure, what happens is that the gravitational field couples both of them, and this induces decoherency in the quantum degrees of freedom. So the coherency is there, and you cannot avoid it because the coherence is proportional to the coupling to the gravity, which you cannot turn it off. Yeah, yeah. Well, well, I I never thought about collapsing models because I mean I really don't like these sort of models. The way I think it is the same thing as classical physics. If I give you a classical system, and but I I don't give you all the details, you have to describe the classical system as a probability distribution in phase space. But then you can measure the system. If you perform measurement on the system, this probability distribution changes immediately to another thing. So the way I see the state vector is just like this: is a mathematical description of the information that I have about the system, and just I. For instance, Bell inequality or teleportation. Teleportation, in order to be successful, uh, Alice and Bob should do some stuff, but Alice should call to Bob. The collapse of the wave function, let us call this, only occurs when Bob gets the call because he got the information. Then he changes the description of his own system. So there's no collapse of the system. It's just, I mean, information, your information changed, and then description that you made about the system, that you make about the system, must change. Yeah, yeah. I really don't know. I never studied collapsing models of the state function because for me, state function is just a mathematical thing that describes information. Ah, okay, okay. If you pick up a one big mass and you put another one that's falling on the gravitational field of this guy, if the gravitational field has quantum degrees of freedom, which means weak field, we can describe this, then the trajectory of this quantum thing would follow a Langevin equation, which is a stochastic description. So this will destroy coherences and everything else. But this because the quantum fluctuations of the field. I mean, how these things get here with classical gravitational field, I still don't know because I mean, I need to understand these results first, and then the next step here I can put superpositions because he is not localized, so I can put superposition whatever and see what happens with these guys interacting just with the classical gravitational field. I think so. I think that the problem is gravity. Gravity destroys everything because of time, because the way we measure time. I think that they will simply destroy superposition. But I mean, that's what I think. Now I have to prove this. It's a very big step. But let us see. With the quantum field, we can create superpositions. And then see what happens with superpositions. Because, I mean, the probability that we have it here is extremely small. Yeah, it's, if I consider a nanoparticle, it's around the 10 to 30, minus 30, the probability of getting a transition. But the problem is that it's not zero. That's the point. It should be zero, but not. Not for a quantum particle that you have in the laboratory, no, but maybe I don't know. I don't know. We'll have to do the calculations of quantum fields and other stuff. No, just a coffee. Thank you, guys.